Cool. So, hello everyone, and welcome from the new session of Surfing the Ocean. Today we're gonna have two talk. One from the first one is gonna be from Baihe, who is a PhD in Berkeley under the supervision of Michael Jordan, who will talk about data acquisition and experimental design. So the floor is yours. The floor is yours.
Okay, thank you for the introduction. I'm Baihe, and today I'm very happy to talk about a recent manuscript, Data Acquisition via Experimental Design for Decentralized Data Markets. So this is a joint work with Charlie, Farnese, Mike, and Ramesh. So today, my talk will be divided mainly into these 6 sections. First, I'll talk about machine learning data markets and the problem of data acquisition. Talk about issues with using validation data sets in data acquisition problem. And then I'll talk about our approach via experimental design. Then I'll briefly talk about the experiment results and conclusions. So yeah, please feel free to shout out if you have any questions. So machine learning data markets are getting increasing attention in recent years. So as we know that the success of machine learning today is largely attributed to the large amount of data in the domains. In many applications, such as healthcare, the data is generated with large costs, so it is important to enable the transaction between the seller of data and the buyer of the data to incentivize the sharing and circulation of data points in the machine learning. So here is a simplified example of machine learning data market. A buyer, for example, wants prediction based on this X-ray image, and they have a budget of $100. The buyer would then query the data marketplace with this prediction task. The data market would then pair this prediction task with a suitable amount of seller data, which is perhaps closely related to the prediction task. And then the buyer would purchase these data points and then train a machine learning model using the selected data. The model can give the prediction on buyer's data. For example, no pneumonia. And then the buyer's payment is split between the data sellers. So in data market, there are mainly 3 stages. First, data acquisition, where the buyer trades with the data seller for the data points. And then the buyer would train a model and then test the model on their test data. So in this work, we mainly focus on the first stage, data acquisition. And we asked the question, how should machine learning data market coordinates the data acquisition process in order to maximize the trained model's performance on buyer's task? So first, let me give some notations. We have some, or the buyer has some training data, has some test data, X test. And there also exist some test label, Y test. However, those labels are not available to the buyer. Otherwise, they don't really need to buy the data. And the buyer also is concerned with the test loss. They also have a budget B. Each seller may have some data point. We denote them as Xi, Yi, and each data point is associated with a price Ci. The task is to find the weights WI associated to each seller data point. Those WI might be 0 and 1 variables indicating whether you select those data or not. It can also be real numbers indicating the sampling probability of data point or the usage of data point in the training algorithm, or even the privacy budgets associated with the data point by the data seller. And finally, using the selected data points, the weights, the buyer is able to train a model F of theta hat of W, where theta hat of W is the parameter in this parameterized model family, and it's dependent on the weights W. So the problem of data acquisition is to find the suitable weights W1 up to Wn based on all those informations, such as the seller data points, the seller's marginal prices, and the buyer's test data and budgets. So mathematically, it can be expressed in this following optimization problem of maximizing, should be minimizing the loss, which is the expected average expected error on the test data subject to the budget constraints. So this problem is closely related to another problem called data valuation. So data valuation is about measure of the value of each training data point to the learning algorithm with respect to the performance metric. For example, in the leave one out method, the value of data point xi, yi is the difference between the value of the whole data set and the value of the set of all data except xi, yi. And data sharply value is also a very popular example of data valuation method, where the value is defined as the as proportional to the sharply value of the data. So similar to sharply values, it satisfies the properties such as symmetry, linearity, and null player. And it's argued that it's the equitable way of doing data valuation. However, there are some differences between these two problems. In data valuation, people care about attributing the influence of training data on validation performance. So it is often done after the data are selected and used in the training. However, in data acquisition, we care about data's usefulness in predicting unseen test data. So it's mostly done a priori before selecting the data. For example, we can see that if we choose the value as negative loss, then the data with the top data value might not be the data that the buyers want. For example, if we select the data with the top value, data sharply value, and use them in a training, they might not yield the best model performance. Furthermore, data valuation is susceptible to overfitting. For example, when the dimensionality is high or when the number of validation data is small, we can see in this simple example that most data valuation method give like Bayer errors close to the random baseline, which means just randomly selecting the setter data.
Can you go to the previous slide?
Mm-hmm.
So what are you showing in the picture? Yeah. So are you evaluating the fact that you're overfitting in the sense that
yeah, so you can see that when the dimensionality is high, like when D is 30, the data valuation method will give a higher Bayer error as compared to the low dimensional case, D equals 10.
okay. Okay, thanks.
Yes, thanks. Yeah, so the problem of data acquisition has some challenges. First of all, data like all the digital goods are infinitely replicable at zero cost. For instance, if someone downloads, like buys a movie, then their friends, their family can also just copy the movie for free. So this means that the data validation must be performed before the full data access is granted to the buyer. Another challenge is the Arrow's information paradox, which says that data's value for the buyer is unknown until they have the information, but then they have in effect acquired it without cost. So this means that the data buyer needs to have certain information on the value of the data, but the value of data itself is certain information of the data. So if the buyer is able to access the value of the data before even paying the seller, they have in effect get those information for free, which is a paradox in the data market. The third challenge is that the assumption of the existence of a central server with full data access is always dubious, because data setters might not trust those central servers for the first reason. Like they may fear that the data might be copied with zero cost. So many existing approaches deals with the problem using validation data set. So we may have some validation data XIV and YIV that is assumed to be drawn from the same distribution as the test data. Then we can have an approximation to the data acquisition problem by directly substituting the test data with the validation data. For example, the DVRL method uses the weights that minimizes the validation error of the predictor trained on those weights as the value of the data point. So here, F sub theta is the predictor or the trained model trained using the weights H phi. And the H phi that minimizes the validation error would be set as the value of the data. Another method called learning agnostic data valuation uses the gradient of the Wasserstein distance between the trained distribution and validation distribution under the metric defined by the distance between the covariates and the class conditional Wasserstein distance between train and validation distribution. However, the approach using validation dataset has some intrinsic issues. For example, the performance would degrade with larger dimensionality and smaller size of the dataset. We have the formal statement that under L2 laws and Miles assumptions, with high probability, the minimax loss of any predictor based on the weights selected using the validation data set would scale to with D over K, where D is the dimension of the covariance and K is the number of validation data set. Additionally, the performance would also rely on the match between the validation and test distribution, which means that they are susceptible to the distribution shift. So now I'll introduce our approach to this problem, which is based on experimental design. So experimental design is a very classic area in statistics. For example, in linear regression, where suppose we give the data yi equals theta times xi plus epsilon, where epsilon are drawn ID from Gaussian. Then the least square estimator is basically M inverse times summation of xi, yi, where M is the information matrix. This least square estimator would give a confidence set of the underlying parameter theta as follows, where in the two-dimensional case, it's basically an ellipsoid. So the linear experimental design is concerned with selecting the data xi's such that the information matrix is maximized in some sense. We see that the information matrix is a D by D matrix. So we need a scalar criterion, a scalar objective to represent what we mean by maximize the information matrix. So there are a lot of classical optimality criteria. For example, A optimality is the trace of the inverse information matrix, which is basically the average axis length of the ellipsoid. And D optimality is the determinant of the inverse information matrix, which is also related to the volume of this confidence ellipsoid. And E optimality is the diameter of this confidence ellipsoid. So in this work, we use test error as an optimality criterion, which is basically the average test error in this linear model. It can be explicitly expressed as the average of xi transpose M inverse xi over all the test data. Sorry. And this framework is also easy to be extended to nonlinear models by linearization techniques such as neural tangent kernel. So formally, our method solves these optimization problem where we minimize the test error. Sorry, this again should be a mean instead of max. So in the objective, Zi and Zi test are the feature embeddings of the covariance xi and xi test. We comment that when we select the weights among the 0, 1 vectors, the problem is a combinatorial optimization, which is NP hard. So in practice, we may relax this to selecting in the probability simplex. So to enable this method to work in the decentralized data market, it's important to establish fast and federated optimization approach of the experimental design weights. So in our algorithm, we maintain the inverse of information matrix, denoted as P of W. And in each iteration, we compute a negative gradient of the design loss, which is the average, sorry, the sum of the test errors. And we apply Frank-Wolf update, where we select the index J sub t that maximizes the negative gradient, and we update W by taking a linear combination between the previous W and the one-hot vector at JT, where those learning rate alpha is either fixed or optimized by line search over the design loss. And finally, we update the matrix P using the Sherman-Morrison formula. And in the end, we return the top K weights based on the budget constraints. So first, we notice that the negative gradient is only dependent on the local data points, like specifically the jth entry of the negative gradient is only dependent on the jth training data. Furthermore, in the Frank-Wolf update, if we apply a line search to find the learning rate alpha, then this optimization problem is also able to be solved using only the local training data z sub j of t, where j sub t is the index chosen in this update. So then we observe that all the update processes, the negative gradient, the line search, and the update of P can all be done using only the local Sarah data and the, of course, the matrix P. So this means that the optimization can be done in a federated fashion, where the buyer may broadcast the maintained matrix P to all the setter, and the setter can update the all these quantities using only their local data without sharing their data to the buyer or any other entities. And this update has d-squared computation and d-communication per round, which is very efficient. In practice, we also observed that a single-step variant of this method achieves relatively good performance while being extremely fast. So in this method, we only take one step of update, which is equivalent to choosing the top K index of the negative gradient at initialization. So here I'll show some experimental results. First, we compare the Bayer errors with existing methods. So in a synthetic data set, we create we sample Gaussian data from 1K, 5K, or 100K, and we can see that in general the Bayer error would decrease with the number of seller data, and in particular, our method is able to achieve lower error than all the other methods. We also test on real data sets, and we use pre-trained clip or pre-trained weights in clip or GPT-2 embeddings and use them as the feature embedding for the model, and we only optimize the final layer of the model. So this table captures the Bayer error on those synthetic and real data sets. And we see that our method is able to achieve the best Bayer error in most of those settings. So our method is also efficient in the runtime. So this figure shows the confidence interval of the runtime in terms of seconds. So I'll give the conclusion. Our federated experiment design-based data acquisition method is efficient and decentralized. It achieves lower Bayer error without requiring the validation data. So thank you for listening, and welcome to check our paper at the following link.
So thank you very much. Are there any questions? I have just one, maybe some naive questions. So like, I don't understand what's the difference. For example, when you present you present two different algorithms. One is multi-step, one is single step. What's the difference? Like the batch, like there's a difference in the batch where you perform your gradient. Like, what's the difference between single and multi-step?
Sure. Let me share my screen. Yes, I can answer it without sharing. So the single step is just performing a single step of the Frank-Wolf update, and then returning directly the top K weights. So it's was basically a fast approximation to the solution of the original problem, and basically sacrifice the performance with like the gain of the running time, the communication.
And
so
okay, and maybe another naive question is like, I don't understand how you solve. Maybe I got lost in the beginning, but how you solve the paradox that you presented before? Like, so how can you assess the quality of the data that you are trying to collect?
Yeah, that's a good question. So since our algorithm is basically a federated algorithm, it does not really require the buyer does not know the seller data in the optimization process. In fact, the seller would perform the update themselves and then send their update to the buyer. So this enables this data valuation without knowing the seller's data. So basically, this federated learning approach itself enables this kinds of data valuation.
Okay. Okay. Okay, well, thank you again.
Thank you.